Hey you guys, welcome back to the Math Fun Room. In this video today we're going to talk about section 5.4 which would be the topic of indefinite integrals. Now I had written on here before we started the reminder of the fundamental theorem of calculus. So in the prior section 5.3 we discovered and discussed what we call the fundamental theorem. Now remember, the idea behind the fundamental theorem basically was that the derivative operation and the integral operation are, let's call them inverse operations. They undo each other. So if I evaluate an integral and then I take the derivative of that answer, I end up right back where I started. So if we look at part one of the fundamental theorem that we wrote here, all right, this is saying that if I integrate some function, let's call it little f, it produces a function called cap f, and the derivative of cap f brings me back to my original function I started with. So again, right, little f produces an antiderivative, we called it, and then if I take the derivative of this function, it brings me right back. So part one just says this in a very general form, that the integral produces an antiderivative. Now part two discusses an integral where we have limits of integration, right? And this was what we did in 5.3 really. When we evaluated the integral of little f, we created the interval of cap f. We created the function cap f and we plug in the limits of integration. So if I had a limit of integration from a to b, we have cap f at b minus cap f at a. So what we're going to focus on in this section is what we call an indefinite integral, and that's really part one. We're going to come back and explore part one a little deeper. So notice I don't have limits of integration here. We call that an indefinite integral. So let's take a look at a real quick example of an indefinite integral, and then we'll do some more intricate, exciting examples here. So our first example, let's say we're looking at the indefinite integral of x squared dx. So again, this is asking, what function do I take the derivative of to get x squared, right? What's my antiderivative? So I know if I'm differentiating a function and getting x squared, it must have been the function x cubed that I took its derivative of. And if I come over here and kind of check my work, we're going to find a little mistake that we just made. And we kind of discussed this already in the prior section, right? But just to take this a little deeper, so if I differentiate x squared, I get 2x. Right? Now the problem is I have a 2 here, if I differentiate x cubed, right, I'm looking at this as my answer. So if I differentiate x cubed, my antiderivative, I would get 3x squared. So my derivative, right, my integrand is x squared. There's no 3 here. So what I need to do really to fix this is put a 1/3. Right? So what I really need in that case, right, is I need to put a 1/3 here. I'm going to say the derivative of 1/3 x cubed. So when I take the 3 and bring it down, the 3 and the 1/3 cancel, if you will. They reduce to number 1, and I end up with just x squared. So when I take this antiderivative, I have the 1/3. Now also what I'm going to end up with is what we call a constant of integration. Because when I differentiate this expression, the derivative of the constant is 0. So I could come back here and I am going to erase, and I'm going to say I could have any constant of integration here, and the derivative of that constant is going to be 0, and it goes away. So this is what we're focusing part of our conversation on in this video. We're looking at what we call an indefinite integral. There are no limits of integration. We're not going from a to b. So what we're producing is an antiderivative, and what we call this is a family of antiderivatives. Right? And the reason we call this a family of antiderivatives is because the constant c can be anything that it wants to be. Right? In other words, if the constant was 5, then I still have an antiderivative that matches. This is 5, 1/3 x cubed plus 5. When I differentiate, I come to x squared, my original integrand that I have here. This constant could be 10. And I differentiate 10 over here to check my work, right? And it goes away to 0. That constant could be pi. So the derivative of pi is 0. And the constant could be any number that it wants. So we're creating what we call a family of curves, family of antiderivatives. Let's take a look at this example where we're finding the integral of secant squared. Now again, this is an indefinite integral because I don't have limits of integration, right? If I look at my integral, I don't have limits of integration. So this is an indefinite integral. So in other words, we are looking for the antiderivative of secant squared of x, right? So we're asking, what do I take the derivative of to get secant squared? And we know the derivative of tangent is secant squared. Right? So then the integral of secant squared gives me tangent. Now, remember, this gives me a family of curves, so I have some constant of integration here. That constant can be any number that it wants, so we have to represent that there could be some constant there. So if I take the derivative of tangent x plus c, I'm going to get secant squared. Right? So the integral of secant squared is tangent x plus c. Again, family of antiderivatives. All right, so when we're doing any of these problems, right, we want to reference our kind of known derivatives, which would produce known integrals. I don't know if you can see this really well. Let me zoom in a little bit. It looked a little fuzzy and cloudy there. So the first one that I want to focus on is, let's look down here at like e to the x, right? What's the integral of e to the x? It's going to be e to the x plus c, right? Because the derivative of e to the x is e to the x. We could look at, what's the integral of sine of x? Right? That's going to be negative cosine, because the derivative of cosine is negative sine, and then we have the negative of that, which makes it a positive here, right? We just saw this guy, right? Integral of secant squared is tangent because the derivative of tangent is secant squared. And then a couple other things we'll point out to ourselves, right? Let's look at integral of 1 over x. Right, I know the integral of 1 over x is going to be natural log of x because the derivative of natural log of x is 1 over x. And then in a more general manner, we have what we could call the power rule here. That if I'm integrating x to a power, I'm going to add 1 to the power and divide by the new power. Right? And so we kind of saw that in our very first example, the integral of x squared. So I add 1 to the power and I divide by that new power. Personally, I like to write this as 1/3 x cubed because it helps remind me that the denominator, right, really 1 over that is the coefficient in that manner. Now, just to explore this a little bit further, notice this says that this is only true, or this is true for all n except -1. So if we think about if the exponent is -1, and if we tried to use the power rule there, right, I'm going to have -1 plus 1, which is 0. I get division by 0. So the power rule doesn't work for -1, right? And remember, -1 exponent is really 1 over x, and so that's the natural log that we have there, right? So we have our table of antiderivatives that we have discussed in the past, and so as we do all of our family of antiderivatives, we really need to come back and reference this list of functions, right? This list of antiderivatives that we technically know already back in 4.9 when we discussed antiderivatives as an initial concept. All right, let's take a look at another example here. So in this example, I want to integrate 10x to the 4th minus 2 cosine x plus 1 over x squared. So technically, when we first start these, right, what we have done in the past is we will integrate each individual piece, if you will, within that integrand, right? Each individual term. Right, so I'm going to find each of these antiderivatives. So again, usually what we like to do is pull the constant out front of the integral. Right? And so we write each of the terms this way. And then just to remind you that 1 over x squared, I need to use the power rule. So I need to write this as x to a power, right? So then I can add 1 to the exponent and divide by that new exponent. So when I do the power rule with x to the 4th, I'm going to get 1/5 x to the 5th. And you know, technically there's a plus c that we get here. I'm going to call it c1. Right? And then we have minus 2, and the integral of integral of cosine is sine of x. And again, technically we get a constant of integration there as well. I'm going to call it c2 because this constant could be different from that constant. And then when I take the antiderivative here, I'm going to add 1 to the power. So this is going to be -1, so I'm going to have 1 over -1. And again, technically a constant there as well. So I'm going to go ahead and simplify my antiderivative. So I have 10 divided by 5 is 2. And then I get -2 sine x from here. I'm going to talk about the constants in just a moment. And then this is really minus x to the -1, which is really 1 over x here. And then what we're going to do is we're going to get a little efficient. So this constant c1 plus this constant c2 plus this constant c3 is really just one big combined constant. So when we do indefinite integrals, we're just going to really do all the antiderivatives, and then at the very end, we're going to tack on this constant of integration. And again, I could write this x to the -1 is 1 over x if I wanted to, and here is my final answer for that function. All right, let's take a look at another example. In this example, I want to involve a little more complex trig functions. So I want to integrate cosine of theta over sine squared of theta. So two things I want to really accomplish in this example. First of all, I wanted to switch the variable. The variable isn't always x. We could have the variable be lots of different letters, right? So here's cosine theta over sine squared of theta d theta. Now remember, this is supposed to be a known derivative, right? So we're asking, what do I take the derivative of to get this expression? And that's not an easy question to answer. So if I scroll back up to my table of known integrals, I don't see that expression cosine theta over sine squared. So what I need to do is a little bit of manipulation of my expression to get it to match one of these. And we really have already done that before in the same concept, right? 1 over x squared wasn't up here in my table, but I rewrote 1 over x squared so that I could use the power rule. So I need to do the same thing here. I need to rewrite cosine over sine squared in a form in which I can handle that expression based on that table of known integrals. So a couple different ways for me to attack this. I'm going to come over here to the right and do a little bit of scribbling. So one thing I could do is I could write this as like cosine theta times 1 over sine squared theta. And 1 over sine is cosecant. So I have cosine theta and then cosecant squared of theta. Now if I scroll back up to my table, I don't see that as an integral. So this initial approach isn't really productive. I don't see that as an integral. So instead of writing cosine times 1 over sine squared, let's try writing cosine over sine times 1 over sine. Right? Obviously I'd get sine times sine, which is sine squared in the denominator. Right? So this cosine over sine is cotangent, and then 1 over sine is cosecant. Aha! That one is productive for me. So I can see that cotangent times cosecant would give me negative cosecant as an antiderivative. So cotangent times cosecant gives me negative cosecant as my antiderivative. So my antiderivative here is negative cosecant of theta, and then plus c as my antiderivative. All right, let's take a look at another example here. So in this example, I have another kind of sum of terms here, and I wanted to mix some different functions together. So I wanted to use e to the x, I used hyperbolic cosine, and then I have 2 over x squared plus 1 is what that's supposed to look like. x squared plus 1. Right? And you know what? Actually, let's do this. Check this out. I don't want to use x here. Let's pick a different letter. Because the reality is, this letter can be anything that it wants. So I'm going to make this e to the u, hyperbolic cosine of u, and then u squared plus 1, and du. Right? So it's the form of the integral that we're trying to match here. So I'm going to split up, just like we did the example, right, 2 examples ago. Right? So I'm really integrating e to the u, I'm really integrating hyperbolic cosine of u, and I'm really integrating 1 over u squared plus 1. Now if we were to scroll back up at our table, we would see that the integral of e to the u is e to the u. And of course the table says e to the x is e to the x. The letter doesn't matter here. And then if I scroll back up on my table, I see the antiderivative of hyperbolic cosine is hyperbolic sine. Now again, the table has x, u is fine. And if I scroll back up again, 1 over 1 plus x squared is inverse tangent. And then we tack on our constant of integration. Let's do another example here. So I changed variable again. I'm using the letter t. And we're integrating with respect to t, my dt that I have here. So in this example, similar to the prior couple examples, I need to simplify a little bit because when I look at my table of integrals, I don't see this formula, if you will, in my table of integrals. So I need to simplify. Right? So what I'm going to do in this case is I'm going to break everything up over the denominator. So here's me splitting everything up over the denominator. Right? All right, now technically I'm supposed to split this into 3 separate integrals. Right? I'm not going to do that. We know conceptually that I'm supposed to do that, but I'm not going to. We'll just talk our way through that. Now I want to do a little bit more cleanup. Right? I have 2t squared over t, and that simplifies to just 2t. And then how do I simplify this middle term? Well, in order to evaluate the integral of a root, like we have discussed prior, I'm going to write that as t to the 1/2, and then it's over t. So I subtract exponents there, get t to the 1/2 minus 1 when I subtract exponents, and that becomes t to the negative 1/2 that I will find the antiderivative of, and then this is still just 1 over t here. So I'm going to find the antiderivative of 2t. Right? I'm going to pull the constant out. Excuse me. I'm going to pull the 2 out. And then the antiderivative of t is t squared over 2. And then when I take the antiderivative of t to the negative 1/2, right, that's going to be t to the, I'm going to add 1 to the power and then divide by the new power. 1 minus 1/2 is positive 1/2. So I'm going to divide by that power. And then 1 over t is the ln of t as an antiderivative, big constant of integration. I'm going to do a little bit more simplification here. Keep in mind this 2 was only multiplying the t there. So 2 times 1/2 is 1, so I get 1/2, and then this is minus 1 over 1/2 is 2, and then this is t to the 1/2, which I could write this as square root of t, and then I get ln of t plus c here. So again, family of antiderivatives because we have an indefinite integral with no limits of integration. All right, so let's again make a connection to an application here. Right? So one of our classic applications is that if we start with a position function, right? So Stuart likes to use the letter S. Right? Letter S might represent the height or position, some location. Right? Usually this is in feet or meters, some unit like that. Let me say meters, whatever that equation is. Now back in the derivative chapter, we talked about velocity. Right? Velocity was the rate of change of position over time. Right? So we were differentiating the h function, and if time was measured in seconds, we would have meters per second there. And then we could take the derivative of velocity, and we could get acceleration as a function of time. Right? That's velocity's derivative. Right? And again, if my unit of time was seconds, I'd have meters per second squared. So with the fundamental theorem, right, we talked about derivatives and integrals are inverse operations. So if I start with position and I take the derivative, I get velocity. And I can go backwards. If I take velocity and I integrate, I come back to my position equation. So conceptually, as we just mentioned there, right, the integral of velocity would give me position. And vice versa, right? If I have acceleration, to get to velocity, I'm going to integrate. So I could integrate acceleration and get to the velocity function. Now keep in mind, I technically have constants of integration here because these are families of antiderivatives. So we could go backwards, right? Derivatives and integrals are inverse operations, and we can move in the other direction in this application of position, velocity, and acceleration. So let's take a look at an example where we might use that process. So in this example, we say the acceleration function in meters per second squared and the initial velocity are given for a particle moving along a straight line. So part A says find the velocity as a function of time. So if we know acceleration is t plus 6 and we know the initial velocity is 2 meters per second, let's find the velocity for any time t. So let me give myself a little bit of extra space here. So just like we talked about just a second ago, right, if I'm going to find velocity, that is the acceleration. Right? So the integral of velocity is my acceleration. Technically, constant of integration there. So for this particular example, we're integrating the acceleration equation that we were given, t plus 6. So if I integrate t, I get 1/2 t squared, and if I integrate any constant, I get constant times t. And again, I have a constant of integration. So keep in mind, this is my velocity equation here, right? You know what? I wrote that backwards. What is wrong with me? Look at that. Goodness gracious. I apologize. Let's take out our eraser and let's fix this. The integral of acceleration is the velocity function. Right? The velocity function is the integral of acceleration. So here's my integral of acceleration, right? That is velocity. Right? So we know velocity is 1/2 t squared plus 6t plus c. Now we're told that the initial velocity at time 0 was 2 meters per second, right? So we're going to plug that in. We're going to plug in t equals 0 and a velocity of 2. So we have a velocity of 2 and we're plugging in t equals 0. And notice what that's going to do for us is find our constant of integration. So I get 0 plus c equals 2. So there is my overall constant of integration. So I have my velocity function. Let me come down here in green. And here's my velocity function. We have 1/2 t squared plus 6t and then plus 2. Right? So we have the 1/2 t squared plus 6t plus my constant of 2. Right? So this is all in meters per second. All right, now part B says find the distance traveled during the given time interval. So I'm going to change colors here. The time interval they give me is from 0 to 10 seconds. So if I'm finding position, right, or distance, right, to find position, that is the integral of velocity, right? So position, right, is the integral of velocity. Now what we're wanting to do in this case is integrate over the given time interval. So we're going to integrate from 0 to 10 seconds the given time interval. Now the velocity equation that we have, that we worked through, is 1/2 t squared plus 6t plus 2. So in this case we're doing a definite integral to find our distance traveled over the first 10 seconds. So I'm going to look at 1/2 t squared. Oops, I got to do the antiderivative. Goodness gracious, this is what happens when you don't drink your coffee. So I have 1/2 t squared becomes, I'm going to get 1/3 t cubed. And then the integral of t is 1/2 t squared. And then 2t. And I'm going to evaluate from 0 to 10. All right, and then just like in the prior section with definite integrals, I'm going to plug in my t value. So what do I have? I have 1/6, I have 10 squared, and then 6 over 2 is 3. Goodness gracious, this is cubed, 10 cubed. And then we have 10 squared, and then plus 2 times 10. And then we subtract. So here's my plugging in the upper limit, and then we subtract with the lower limit plugged in. So I'm going to plug 0 into my antiderivative. And notice what's going to happen. I'm going to get 0 cubed plus 0 squared plus 0. So that's a big old 0 that we're subtracting. All right, so evaluating all of that, I get a distance traveled of
approximately 487 meters
as my distance between 0 to 10 seconds. Now, in this last example, I'm going to point out to you something that is slightly different, right, between a definite integral and an indefinite integral. Now, if I take a look at letter C, we were evaluating a definite integral, right? It had limits of integration. And as is always the case, right, as what we should have noticed in the prior video for 5.3, when we evaluate a definite integral, we get a number, we get a numerical measurement. But when we evaluate an indefinite integral, we get a family of functions. So again, in part A, we evaluated the indefinite integral, no limits of integration, and we don't get a number, we get a family of antiderivatives. So in this section, we want to kind of summarize the difference between the two. Integrals and indefinite integrals produce families of functions, not numerical values. Definite integrals will produce numerical values. So the last thing we want to look at in this video, in a section of this nature, where we're talking about indefinite integrals, we want to come back really and look at what we call a definite integral. So one of the applications, which we've really already looked at, but we're just going to revisit a little more formally here, is what we call the net change theorem. Now remember, this is really part 2 of the fundamental theorem of calculus. So part 2 basically told us how to evaluate a definite integral with limits of integration. And one way we can interpret this integral is as what we call a net change. Now the other way that I like to write part 2 of the fundamental theorem is this notation down here. Now keep in mind that I'm integrating a derivative. Right? When I find the antiderivative of this function, right? So this is the rate of change. So my antiderivative has a derivative of the function f prime. Right? So if I'm integrating a rate of change, it is telling me about the net change of the original function. All right, and what the heck does that mean? All right, so the idea, there's actually lots of different applications of this idea of net change. In fact, actually, our distance problem that we just did was exactly that. Right? I integrated the velocity function, and it told me the change in position, which is distance. Right? So whenever I integrate a rate of change, remember velocity is the rate of change of position. So I'm integrating the derivative of position, and that's giving me the net change in position, 420 meters in this example. So if I bring up, again, this is Stewart's calculus book, right? Other applications of the idea of rate of change, he presents to you here just as a bigger picture, right? What's one application of integrals? Right? There's multiple applications. In the net change theorem, we can see what some of those applications are. So first example he looks at, he says if V of t is the volume of water in a reservoir at time t, then its derivative V prime is the rate of change of volume per unit time. So if I integrate the rate of change of volume, it's going to give me the net change in volume. Right? Taking the antiderivative here, and it's giving me the volume function. If C of t is the concentration of product of a chemical reaction at time t, then the rate of change of that reaction, we would denote dc dt, right? Its derivative. So if I integrate dc dt, my antiderivative is the concentration function, and this is giving me net concentration. Back in the derivative chapter, we also talked about how density, right, linear density of an object is the change in mass per change in length. So if I have a mass function, m of x, right, its derivative, the change of mass per change of length, we called linear density. And we used lowercase Greek letter rho to represent that idea. So if I'm integrating m prime, or if I'm integrating linear density, that's giving me the change in mass as I move from point A to B on the rod of mass. I have a rod made up of metal. If I have a population n, its rate of change, its growth of the population, dn dt. If I integrate the rate of change of population, if I integrate the growth rate of the population, that's going to give me the net change in population from one time to the next. So we have 5 or 6 examples you would see here where the net change theorem is within an application giving me the distance traveled, right? Or the difference of mass, right? Or the difference of concentration, right? The change in concentration. Or the change in volume from one time to the other. Now, just like the prior example we did, right, some of the problems in a section like this, you would be given the equation. So in this example, letter B that we did, right, we have the equation which is the derivative of S, right? So I'm going to, just kind of grab my pen here, right? So the position of the function is the integral of its rate of change, right? So when I go from 0 to 10, the integral of velocity gives me the change in position. We called that distance. Now, some of the problems in a section like this, you will have the equation of the rate of change. And in this case, we did have the equation. We don't always have the equation. Sometimes we have just numerical data. Let's take a look at an example like that. So I took this example out of Stewart's textbook. This is problem 65 in section 5.4. And this problem doesn't have an equation for the velocity. It just has numerical table of data. This problem says the velocity of a car was read from its speedometer at 10-second intervals and recorded in the table. It says use the midpoint rule to estimate the distance traveled by the car. Now, if we take a look at this table here, well, again, we don't have a graph. Now, I could kind of visualize the graph. This is not really what we need to do for this problem, but just to make it visual, right? I'm a visual learner. So let's say this is my time in seconds, and then this is my velocity, right, in miles per hour. Miles per hour here, right? So if I were to graph these points, at time 0 my velocity was 0, at time 10 my velocity was 38, let's say that's roughly there. At time 20 my velocity was 58, let's say that's there. 52. At time 30 it was 58. Let's say roughly there, right? At time 40, my speed was 55, and let's say roughly there, so on and so forth, right? So here's the points on my graph. T equals 50, I'm at 51, T equals 60, what was I at? I was at 56. All right, I'm going to stop plotting the points here. So what we want to do, right, as we just discussed, is the distance, right, the distance that we travel is the integral of the velocity function. Now, I don't have the equation of velocity, but I do have its numerical data. And this problem is saying use the midpoint rule. Use the midpoint rule. So what we're envisioning here really is like, areas of rectangles like we did back in the 5.1 section. So if I'm doing midpoint, what I'm going to do is if I look at like this first interval, let's say I'm going from 0 to 20, 10 is its midpoint, and that's going to generate the height of the rectangle here. Oops, I don't want that line to go all the way up. There's my rectangle. So from 0 to 20, 10 plays the role of the midpoint. And then I could go from 20 to 40, and I didn't line these up really well, right? But that would be my midpoint for that next rectangle. And then if I go from 40 to 60 at 50, that would be the midpoint of my next rectangle, so on and so forth. So the height of every rectangle is at the midpoint, at 10, at 30, at 50. So at 10, at 30, at 50, at 70, at 90, those midpoints give me the height of every rectangle. And then my delta x, right, so my distance between the two, in this case is going to be 20. Right? So from 0 to 20, there's my delta x of 20. Right? From 20 to 40, there's a delta x of 20. So if I were to use midpoints, right, I'm doing, length times width, if you will, right? Width times height. So my delta x is 20. My height is whatever I get at the midpoint. Now remember, the delta x is 20 for all of these rectangles. So what we can do is we can factor the 20 out. And then we'll add up all of the midpoint values. So we're going to have 38 plus 58, 58 plus 51 plus 53 plus 47. All right, and I took out my calculator and I added all these numbers together, and I got 20 times 247. Now, before we give our final answer here, something I want to point out is that we have a mismatch of units. Remember that my time is in seconds and my velocities are miles per hour. So we have an issue here, right? I have seconds times miles per hour, right? So my time units aren't going to cancel, if you will. Right? Remember, I need my time units to cancel so that my distance traveled is just miles. So I have a mismatch of units. So it's the x units that aren't matching. I need to convert these x units to be hours, not miles. So I'm going to come over here and I'm going to convert my 20 seconds into hours. So let's see, I want to cancel the second and I want hours. Now what I'm going to do is I'm going to take a step. I'm going to do seconds to minutes, and then I'm going to cancel minutes with hours. So let's see, there's 60 seconds in each minute, and then there's 60 minutes in each 1 hour. So I would see in this case the seconds would cancel, the minutes would cancel, and I would end up with hours in that case. So 20 divided by 3600 would be the conversion in terms of hours. I'm going to switch to red, so my 20 seconds is really 20 over 3600 hours. And then we have our 247 hours, and when I multiply those out, I'm going to end up with miles as my net distance. So doing that on my calculator, I'm going to approximate as a decimal. I get 1.37 miles traveled there. So that is really everything to discuss in this section. I will see you in the next video.